Building modern interfaces requires a constant tension. Systems must continuously balance three competing forces: privacy, performance, and personalization. Traditional software architectures manage these trade-offs by flattening three distinct variables into a single arithmetic average, a top-line overall health score. If privacy protections crash to zero, but performance spikes, the average remains stable, completely hiding the localized failure. When building autonomous, agentic software, a hidden failure is catastrophic. If an AI agent requires strict ethical gating to protect user data, an arithmetic average will authorize execution even when critical safeguards have collapsed. To construct sovereign interfaces, we have to stop hiding these failures behind averages. We need an architecture that measures actual structural tension between competing priorities. This is the Marshall Triangle. It is a formal geometric framework built specifically to solve the problem of flattened, multi-objective trade-offs. Instead of averaging variables into a single number, this framework maps privacy, performance, and personalization into a continuous, two-dimensional triangular domain. It preserves the exact state of all three axes simultaneously. Secured under pending U.S. Utility Application Number 19734-975, this is not a conceptual diagram. It functions as the actual governing computational architecture for the system's interface. Notice the glowing white point at the center. Unlike rigid graphs with a fixed origin, this dynamic center of equilibrium emerges directly from the field's active tension. System architects use this framework to model and execute operations based on competing priorities, maintaining the mathematical integrity of the underlying data. Standard simplex models, like traditional color spaces, place their primary variables strictly at the corners, or vertices. This severely restricts how variables can blend across the geometry. The defining geometric innovation of the Marshall Triangle is an inversion of that standard. The primary system axes are anchored directly at the edge midpoints. Red is assigned to privacy on the left edge, green anchors performance on the right, and blue anchors personalization at the bottom. By placing sources at the midpoints, the extreme tips emerge as secondary states, like yellow, a blend of only privacy and performance. Moving the anchors to the edges creates a continuous internal field of influence. This allows for infinite, smoothly blended interior states, where all three variables interact. A static graph becomes a dynamic, bounded coordinate space. Every rendered pixel inside the triangle corresponds to a precise, mathematically verified ratio of system balance. To operationalize this geometric balance, the system translates the current state into strict mathematics using a normalized state vector. This equation is the geometric harmony index. It calculates the exact displacement of the system away from perfect equilibrium. The current state is plotted as vector p. Perfect balance is point U, at coordinates 1/3, 1/3, 1/3. The line connecting them is the Euclidean distance. This distance represents tension magnitude. The further the vector strays from the center, the higher the mathematical tension. The geometry provides a mathematical mapping of system stress, converting abstract priorities into a calculable displacement vector that downstream software can read continuously. That theoretical geometry translates into the actual runtime codebase that governs the application interface. This formula shows how the code calculates the final scalar threshold. Instead of an arithmetic average, the codebase uses a strictly bounded harmonic mean. A harmonic mean disproportionately penalizes the lowest performing component. Watch what happens in a critical failure scenario, where privacy crashes to a near-zero fraction, while others remain high. The harmonic mean plummets instantly. This calculation accurately reflects the system compromise. This specific codebase choice establishes a hard, reliable threshold for system coherence. It guarantees that a single poorly aligned axis cannot be hidden by the performance of the others. The rigor of the codebase is immediately visible to the user through client-side SVG graphics. The smooth, continuous gradients filling the triangle are calculated using a weighted radial falloff function. Specifically, a Gaussian falloff is applied, originating from each midpoint source. Before drawing to the screen, a normalization step translates raw simplex values into RGB pixel space, preventing color clipping at the extremes. Here is a comparison of three distinct states, reintroducing the white point. This point is the direct visual representation of neutral recombination within the rendered Gaussian field. The white point is dynamically field-derived, not a static geometric center. It visibly shifts its physical location based on active priority weighting. When comparing dual-axis emphasis with a single-axis privacy state, mathematical tension pulls the white point toward dominant anchors. This rendering process produces a real-time, mathematically accurate color field that tracks the exact tension of the user's current settings. The mathematics of the Marshall triangle drive the system's internal operations. It functions as a constitutional geometry. Its internal mathematics dictate actual system behavior and autonomous execution. The displacement vector and the final harmony index score are exposed as first-class outputs in the computation pipeline, available for downstream software modules. This flowchart shows the primary consumer of these metrics, the system's shared autonomy observer. The exact same math rendering the visual interface is simultaneously making autonomous system decisions behind the scenes, unifying UI and system architecture. The shared autonomy observer uses the harmony index as a strict pass-or-fail execution threshold. If system tension drops below a configurable threshold due to compromised privacy, the observer immediately blocks execution on external cloud compute nodes. The system automatically reroutes the requested action to a local, sandboxed mesh environment, ensuring the user's data integrity is protected. This gating mechanism also controls AI model selection, dynamically authorizing or revoking agent execution privileges in real time, based strictly on triadic balance. This configuration allows the system to verify its own internal alignment before executing an external command. By anchoring priorities at midpoints and guarding them with harmonic means, the Marshall triangle allows autonomous systems to navigate trade-offs while adhering to strict execution thresholds.